Yeah, good morning, every one of you. So until the last class, we are seeing this unit 1, diffusion. So some of the topics we have covered, and we are seeing units. Okay, various different type of quantities are there, whose units, okay, how the additive properties will be there. We are seeing that one. Today we will continue that one. And then first law of diffusion we will discuss. Then this properties we will cover today. So let's see. Yeah, this properties we are seeing mass, volume, molecular weight, moles. So once again, newly we will cover this. I hope you understand this. What is molecular weight? Why can't we write Ma plus Mb? Only we have to use average molecular weight relationship, which we have seen in CPP course. So once again, quantities I am writing. So the quantity is first one. Quantity, then units. Okay, its symbol also we'll write separately. Let's try to write it separately. Symbol, then its units. For symbol for its component A. For its component A symbol, then what is that quantity for component B, and total mixture for total mixture. We have, I repeat once again, we have in a system only two component system, that is A plus B. Okay, you need not to bother about any other component. Only two components are there in system. That makes our system as very simple. So first quantity is mass. We know the symbol of mass is small m we are using, and units of mass is kg, gram. In SI units is kg. Then component A, we will denote it as small m subscript capital A, and for component B it is small m subscript capital B. And for the total mixture, okay, can anybody please respond? Can you see my screen?
Yes, sir.
Okay, yeah, thank you.
Yes, sir.
Okay, thank you. Okay, then the total quantity, which is the additive property, mass is, so m is equal to small m A plus small m capital B. So this is the additive property. Then next one we can write volume. So volume is denoted by capital V. So for each species we will be giving only I value. So okay, I can take A and B quantities, or one or two, one and two also we can use depending on whatever we prefer. So volume is measured in meter cube in SI units. Then component A, it is capital V subscript capital A, and for component B it is capital V subscript capital B. Then this is additive property. Volume is also an additive property. So we can write capital V is equal to VA plus VB. The next one we can write velocity. So velocity is denoted by small u subscript small I. Then velocity is measured in meter per second. Then for component A, it is ui subscript small I, then small u subscript, sorry, this is A, ua, then this is ub. Then this is a vector property. So velocity is a vector, not, it is not a scalar quantity. We cannot add that one. It is a vector. Whenever we are giving some quantity to a vector, we have to specify its direction. In which direction this component is acting, x, y, z. So that's why we will leave this as such. Then next quantity will be molecular weight. Molecular weight. So it will be denoted using capital M subscript I. So I can take a value of A and B. So molecular weight, we know the units kg per kg mole, or gram per gram mole, whatever it may be, lb per lb mole. We can use anything. So molecular weight is denoted by Mi. Then for component A, it is M small capital M subscript capital A. Then for component B, it is capital M subscript capital B. Then this is also not a additive property. So because of additive property only, but we cannot use as such Ma plus Mb. But this is, we have to use average molecular weight. We have to use, or we can denote it as MW average. We can denote. So MW average will be sigma I is equal to 1 to n xi into capital Mi. So mole fraction into molecular weight is nothing but your average molecular weight. Then next quantity we can write moles. Okay, since moles is coming under this basic quantities, okay, basic units, okay, not a derived unit. So moles will have a units of mole only, but the notation scheme we will use is small n subscript small I. Then mole will have a units of mole, since this is a basic unit system of basic quantity. Then for the component A, it will be small n subscript capital A. For component B, it will be small n subscript capital B. Then this moles, since this is also additive property, we can denote n is equal to capital small n is equal to, for component A, Na plus Nb, or otherwise we can write moles is equal to mass. Okay, overall moles is equal to, we can write individual moles, sum of the individual moles, but we can write mass divided by this average molecular weight is also the mole definition. We know that in CPP you have seen moles is equal to weight by molecular weight. Similarly, this is a total mixture quantity. We can write total mass of this mixture is small m, then average molecular weight is MW average. We can write this as small m divided by MW average. Okay, either of the case you can use. You can find out individually like this Na and Nb, then sum it up, or otherwise you can find out the total mixture mass divided by average molecular weight of that particular mixture. We can do either of the way. Then if there is a moles, then we can define mass concentration. Mass we have defined, no? We will define mass concentration. So it is similar to the density. Okay, whatever the density units will be there, the same units will be there for the mass concentration. So that is rho I. Okay, mass concentration is denoted by rho I. Then the mass quantity will concentration will have a units of kg per meter cube, which is same as the density units. Then for the component A, it is rho subscript capital A. For component B, it is rho subscript capital B. So these are the individual mass concentrations or densities of that particular component A and component B. Then we can write for the overall mixture, density or mass concentration is equal to rho A, sum of the mixture quantities, which is rho A plus rho B. Or otherwise we can write as density is equal to mass by volume. We know that one. For the total mixture, total mass is small m divided by capital V. Okay, mass by volume is nothing but your density. We know that from CPP, rho is equal to mass divided by volume. Same quantity we can write. So overall total mass of the system is m, total volume of the system is V. So we can do for the total mixture in this way or in this way. Individually we can find out the mass concentration of A and B and we can sum it out. Then next one is a molar concentration. Now mass concentration is defined. Then we will define molar concentration. So molar concentration. This will be denoted by C, small c, subscript small I. So concentration, molar concentration is nothing but simply we can say it is a concentration. Concentration will have units of mole per meter cube. So you just remember, if this is a mass concentration, then mass only the numerator will be different, kg. If this is a molar concentration, then in the numerator it will come mole per meter cube. This is normal concentration only. For component A, it will be denoted by C subscript capital A. Then for the component B, it is C subscript capital B. Then for the total concentration, C is equal to sum of the individual concentration Ca plus Cb. Or otherwise we can define as this, you see mole is nothing but N. Okay, this one. The unit of mole is this one N. Then overall mixture N is this one. Then meter cube is the unit for volume. So total mixture volume is denoted by V. So we can write this as N by V. So okay, total mixture moles divided by total mixture volumes. You can calculate this way also, you can calculate individual way also. Either of the way is correct only. Then mass concentrations are there. Then mass fraction we will calculate. Mass fraction. So mass fraction will be denoted by, we will say this one, Wi. Okay, Wi, mass fraction. Then the units of mass fraction is, there are no units for the mass fraction or mole fraction because they are only fractions. Then this for component A it is W subscript capital A, and for component B it is W subscript capital B. Then this is also an additive property. So we can write W is equal to WA plus WB. Sum of the mole fraction or mass fractions is always equal to 1. We have learned this principle from CPP course. So sum of the mole fraction or sum of the mass fractions is always equal to 1. If there are n number of components, for n number of components also it is always equal to 1. If there are only one component, that is a pure component, so its mass fraction will be always equal to 1. So we can write this as 1, or otherwise we can say total mass divided by total mass. That is also, when you cancel this one, you will get 1 only. So that's the definition of this mass fraction. Then next quantity is mole fraction. So mole fraction from the CPP, we are denoting it with small x subscript small I. Then the mole fraction will not have any units. So for component A, it is small x subscript capital A. Then for component B, it is small x subscript capital B. Then sum of the mole fraction is nothing but, total mole fraction is nothing but x is equal to xa plus xb, which is always equal to 1. Sum of the mole fraction in any component system is always equal to 1, or otherwise we can write total concentration of a mixture divided by total concentration. When you cancel this one, only 1 we will get. So sum of mole fraction or sum of mass fraction in any type of mixture is always equal to 1. You remember this one. The next important quantity is flux. Okay, in the Fick's first law of diffusion, we have written this one, flux. What is the flux? We have defined there. So flux is nothing but moles of component, okay, whatever the component, whether it's a or B, moles of that component transformed from one phase to another phase or from one place to another place per unit area per unit time is nothing but flux definition. So that is the denotation of flux is Ni or Ji, capital Ni, capital N subscript small I, or capital J subscript small I. So what is the difference between this J and N? I will describe in the next topic. So this will have a units of mole per meter square second. By the definition of the flux only, we can write the this unit. So moles of component has been transformed from one phase to another phase per unit time per unit area is called as flux. So this is the units of flux. Then for the component A, which is denoted by Na, or we can say this is Ja. Then for the component B, we can denote as Nb or Jb. But here in the total flux, we can write N is equal to Na plus Nb. Okay, we cannot write J is equal to Ja plus Jb. Okay, this quantity is different, though it is flux. Okay, though J is also a flux, but different coordinate systems will be there. So that we have to define that coordinate system. Then only we can write what is the mixture J property. Okay, but N we can write, it's an additive property, Na plus Nb simply we can write. But we can't write J is equal to Ja plus Jb. You remember this one. Then in the next topic we will cover what is this J quantity, what is that N quantity, what is the difference between them, and what is the relationship between them also. We will cover. Okay, until now, any doubts in this unit systems?
Clear, sir.
Yeah, thank you. Then next same I will show you here. Okay, in the PPT also all these units has been given here. Okay, you can refer PPT. Okay, here every unit is given. So reaction rate we will neglect. Okay, only one unit left here. Reaction rate is usually you will see in chemical reaction engineering course, that you cannot see here, but there is a small part about that one. So this you can see here. Then next we will see what is the Fick's first law of diffusion. In Fick's first law of diffusion, the flux is denoted by Ja. Why it is denoted by that one, I will tell you this. Then we will see what is the What are the two types of fluxes, N and J, and what is the relationship among them? We will define that one. So these are the quantities. Then Fick's first law of diffusion. Once again, I am revising that one. Fick's first law of diffusion. So Fick's first law of diffusion will be, according to Fick's first law of diffusion, flux is directly proportional to, okay, concentration gradient, dou Ca by dou x or dou y or dou z, whatever it may be, for component A. For component A, we can write this as a JA. Okay, this we can write dou Ci by dou z. This is common. Okay, according to Fick's first law of diffusion, flux is directly proportional to the concentration gradient, whereas the proportionality constant in this equation is flux is equal to proportionality constant is DAB. Okay, DAB or DIJ we can write. Okay, only two component system are there here, so we can write Dij. So this minus is there already here, this minus I am writing here. Then dou Ci by dou z. Okay, you try to understand this formula first. See, according to the Fick's first law of diffusion, flux is directly proportional to the concentration gradient. So in order to compensate, okay, for flux, this mass transfer will take place from high concentration to low concentration. We are compensating this fact with minus sign. Okay, minus sign will be there as such, but the proportionality constant will be diffusivity. So I and J, where we can write I and J are individual components. Individual components. Okay, like A, I will take, I will be A, J will be B, or when mass is transforming from A to B, okay, A to B, we can write I is equal to A, then J is equal to B. When mass is transforming from B to C, B to A, then we can write I is equal to B, J is equal to A. So this is nothing but this one. From this to this, the mass is getting transformed. The meaning of this one is, so in this case, the D will be DAB. So DAB means DA to B, that is. So mass transfer is taking place from A to B. And in this case, this DBA. So DBA. The meaning of this one is the mass transfer is taking place from B to A. So the meaning of this one will be this one. So for component A, we will see how to apply this component A, Fick's first law of diffusion. So directly we will apply using this formula. For component A, this will be J in place of I, A will be coming, is equal to minus D, I is equal to A. Then the mass has to be transformed from one place to another place. There will be some minimum two component system in order to get a mass transfer. So J will be obviously B. Then we can write dou C, I means A, divided by dou Z. Then for component B, so JB is
Sir,
equal to, yes,
dou z place it will comes dou a.
dou Z,
Dou z place లో dou a వస్తుంది sir.
dou A na, A ఎక్కడ
Dou
ఉంది
x
అసలు?
x. Dou x
X, we can write dou X or dou Y or dou Z. Okay, whatever the spatial coordinate system, X, Y, Z. So I already said you initially, we are assuming only two component system and also one dimensional.
One
Okay, you can
dimension.
choose. Yes. Catching my point?
Yes sir, yes.
Yeah, one dimensional means any one direction you take, X or Y or Z. Okay, you can write, if you are comfortable with that one, we can write that one only. Only one dimensional, any one spatial coordinate you can take. Dou X or dou X. You can write anything. Okay, is that okay now?
Yes sir.
Yeah. Then this will be DBA, since this is B component. JB is equal to DBA dou CB divided by dou x. Okay, whatever the quantity, we can write like this for component A and component B. Fick's law of diffusion, this one. Okay, this is about Fick's first law of diffusion. Now here in the Fick's first law, each quantity we will just expand that one, where Ja is equal to flux. Okay, whether it's a mass flux or the what we say molar flux. Okay, flux defined with respect to, okay, some we will say this, some with respect to some arbitrary coordinate system. Arbitrary coordinate system. So this x, y, z is nothing but a coordinate systems only. Some arbitrary coordinate system. Okay, for the time being, just leave it like that, or arbitrary coordinate system. In the next topic, we will discuss what is this arbitrary coordinate system and what is the fixed coordinate system. So then the flux will have a units of, we already know flux will be mole per meter square second. If you have any doubt, you can refer to the table. Okay, here mole per meter square second. Then the next one is this one, where DAB, or together we can say DBA, or diffusivities or diffusion coefficients. Diffusion coefficients. So whose units will be meter square per second. The next one is CA. Okay, C subscript capital A is concentration of component A. Component A. Then concentration units will be mole per meter cube, or if it is a mass concentration, it will come rho A. Okay, in place of CA, rho A will come. Then its units will be kg per meter cube. Then CB is concentration of component B. Units will be same, mole per meter cube. Then we can write X or Y or Z is distance. Distance or diffusion path or mass transfer path, we can say. Diffusion path, whose units will be meters. So what is the meaning of this diffusion or mass transfer path? For example, A is there this side and B is there this side. So A has to diffuse into component B. Okay, this A has to diffuse into component B. So the A particle has to travel from this location at a zero origin point. Then it has to go to the B location, that is Z or X or Y, in this direction. Okay, whatever it may be. If the component A is located here and component B is here, the mass transfer is taking place from bottom to top. Okay, diffusion is taking place from bottom to top. Then the origin of that particle is here, and the origin and the completion of that particle will be, for example, it is Y. Okay, 0 to Y. This is X. Okay, 0 to X, this one. Then in the Z direction, for example, A will be having like this, and A has to travel from A to B location. Then here the origin will be 0, and here the completion of that particle diffusion is Z. Okay, whatever it may be, the distance which is traveled from origin to the completion of the mass transfer process is nothing but that distance, this one, X or Y or Z. Whatever the direction you take, only one direction you will take, X or Y or Z. Okay, not all the three directions. This is not three-dimensional, only one-dimensional. That's why we have to take either of the case, X or B, Y or Z. So this is the diffusion path, which is denoted by M. Then the same Fick's law we can write for the pressures also, partial pressures also. So why we have to write partial pressure? For calculating concentration, for evaluating concentration in liquid phase, Ca is equal to moles per unit volume. So estimation of moles, okay, moles of liquid will be very easy. Okay, there is a device or something, moles we can easily estimate using stoichiometry also. But for the gases, okay, this relationship is very much valid for the liquids. For what about the gases? So for the gases, it is very convenient to measure pressures, partial pressures. Okay, in that case, what we will do? We will apply ideal gas law. What is the ideal gas law? Ideal gas law is nothing but PV is equal to nRT. You know, you better know this one. So PV is equal to nRT, where P is a pressure, V is a volume, N is the moles, then T is a temperature. Then this R is a universal gas constant. Universal gas constant. Okay, so this is PV is equal to nRT. So ideal gas law equation. For gases, this ideal gas law equation is very much valid. So from this one, we can deduce the concentration definition of for the gases. So how we can deduce? For example, we can write this relationship as N by V. Then P will be going to the RHS side. So that will be P by RT. So we know already N by V is nothing but C. So concentration is equal to N by V is equal to P by RT. Then for the component A, we can write Ca is equal to Na by V is equal to Pa by RT. For component B, we can write Cb is equal to Nb divided by V is equal to Pb by RT. In this case, this P is partial pressure. Partial pressure of component A. Then in this case, this is also partial pressure of component B. Then in this case, this is overall concentration. Then this will be total pressure of component B. For the gases, it is very convenient to measure pressures. Okay, instead of moles of gases, if you know the pressures, partial pressures or total pressures, then it is very easy to calculate moles. But for liquids, there is no ideal gas equation. In the definition itself, there is a gas. For the gases, this relationship is valid. For the liquids, we can easily measure moles. Okay, I hope it is clear until now.
Yes, sir.
Yeah. Then using this one, so yeah. Then this
Yes.
R value. Okay, I forget earlier I told you I will cover this one R values. Okay, what is this R value? Universal gas law constant. For example, we are using this PV is equal to nRT. We know that partial pressure. So it will be having, it will taking place some units of atma, okay, or Pascal or mmHg. Okay, this will be the units for this one. Then volume units will be some meter cube or liter, or whatever we can write, mm cube we can write, okay, centimeter cube we can write, okay, whatever we want you can write. Then okay, many units you can write. Then next one is moles. So moles will have a units, gram moles, kg moles, whatever the moles will have a units. Then R will have separate units. What is the question mark here? So R will have a different units depending on the PVNT system. So okay, what type of units we are using? The four quantities that defines the R value and as well as its units. So temperature will be measured in degree Kelvin, degree centigrade, degree Fahrenheit, degree Raimur, degree Rankine. Okay, all these units can take the pressure, temperature units. So depending on its units, we have to apply this one from the ideal gas law equation. Okay, from the ideal gas law, what from the stoichiometry of any equation, what it is saying is any gas at standard temperature and pressure. Okay, any gas at standard temperature and pressure will occupy, when it is occupying some container space, so it will be having a constant volume of 22.414 liters. Okay, its volume will be equal to 1 mole of gas. Okay, 1 mole of gas will occupy 22.414 liters at STP conditions, standard temperature and pressure conditions. I hope you know this definition, what is STP and what is NTP. So STP is nothing but standard temperature and pressure conditions. Then NTP is normal temperature and pressure conditions. So what is the STP conditions? Can anybody say what is the STP conditions? What is standard pressure and what is normal pressure? Okay, I will only tell you. So standard temperature is nothing but 0 degrees centigrade is the standard temperature. Then standard pressure is nothing but 1 atmosphere. Then normal temperature and pressure is nothing but our room temperature, 25 degrees centigrade, and normal pressure is 1 atmospheric pressure. So these are the STP and NTP conditions. Using these conditions, at this STP conditions, any gas, okay, any gas will occupy 22.414 liters at only standard temperature and pressure condition. So standard temperature and pressure condition is 0 degrees centigrade and 1 atmosphere. So this fact, STP condition facts, we can substitute in this equation. So let us see. So PV is equal to nRT. So R is equal to, from this equation we can write, implies R is equal to PV by NT. So what is the P at the standard temperature and pressure conditions? 1 atmosphere. And volume is 22.414. 1 mole will occupy 22.414 liters. So 22.414 liters. So that is for 1 mole into temperature. At standard temperature and pressure condition is 0 degrees centigrade. Okay, 0 degrees centigrade plus 273. So degree centigrade plus 273 is equal to Kelvin, or accurately we can say 273.15. So degree Kelvin is nothing but, so degrees will not be there for Kelvin. So this is Kelvin. Degree Kelvin is equal to degree centigrade plus 273 is equal to you will get in Kelvin. So 0 plus 273. Okay, thus 273 I have written here. So if you calculate this one, 1 and 1 will cancel. 22.414 divided by 273. Nearly you will get this as 0.08206 something you will get. So we can write 0.0821. So units are atma. So this one, then this is liter, then this is mole, then this will be in Kelvin. So R value will be, the basic R value will be this one. R is equal to 0.0821 atma liter per mole degree Kelvin. So if you want to convert this into other units, okay, we know that R is equal to 0.0821 atma liter per mole degree Kelvin. For example, if you want the pressure in Pascal, okay, this liter in meter cube, okay, SI units you want, then what happens in the SI units, okay, system international units, we know that pressure will be measured in pascals and temperature will be measured in Kelvin, and this volume will be measured in meter cube. Okay, this we know that one. Then we have to convert this into SI units. How to convert? Okay, we know that 1 atma is equal to 760 mmHg. Okay, we know this one. Then 1 atma is equal to 101325 pascals. 1 atma is equal to 101325 pascal. Then also for the liters to meter cube, 1 liter is equal to 10 power minus 3 meter cube. So these are the conversion units. So for this one, what we will do, convert this 0.0821 into pascal meter cube mole degree Kelvin. So these two units we have to change. So in place of atma, we have to write pascal. So to write that one, so we have to multiply this with 101325. Then this atma will be converted to pascal. And to convert this liter into meter cube, so we have to multiply. Okay, liter is in numerator, so we have to multiply it with 10 power minus 3 meter cube. Then this liter will turns to meter cube. Then divided by mole will be the units, SI units for moles. Then mole, and Kelvin is the SI units for temperature. So this, if you do something, you will get 8.314. Okay, please, if you have a calculator, you just verify this one. 8.314 meter cube, pascal meter cube per mole degree Kelvin. Okay, 1 pascal, we know that this one. 1 pascal is equal to 10 power minus 3 kilopascals. Or in either way, we can write 1 kilopascal is equal to 10 cube pascals. So we have to multiply with the 10 cube to get a kilopascal. 10 power minus 3 to get a kilopascal units here. Okay, is that clear? R values, like this R values we have to calculate. In the problems, this R value is very much used. R is equal to 8.314 Pascal meter cube per mole Kelvin or 0.0821 atmoliter per mole Kelvin. These two R values are very much used in our mass transfer problems. Okay, if you can derive using these facts, you can derive, or otherwise you just remember, try to mug up this one, or otherwise in the notebook I have given around 13 something R values. You can remember. Is that clear? All these conditions?
Yes,
Yes,
sir.
sir.
Clear, sir.
Okay, then next topic will be fluxes. Okay, different types of fluxes.
Yes,
Okay,
sir.
there are two fluxes are there. We know that one. So that flux is Ni or Ji. So what is the difference between these two? So I am writing a basic definition here. What is Ni and what is Ji? Ni is a flux defined with respect to fixed coordinate system. Fixed coordinate system or fixed reference framework, or we can say fixed reference framework. Then Ji is a flux defined. So I am writing a short form with respect to, okay, with respect to arbitrary reference framework. What is this arbitrary? What is this fixed? We will define. So arbitrary reference framework or arbitrary coordinate system. So for example, if there is a gas diffusion, okay, if there is a gas diffusion or gas absorption, okay, the gas will be there here. So gas will be entering from bottom to top. Okay, it will be leaving from the top. This is gas inlet. This is gas outlet. Then to exchange a mass, there will be some liquid we have to give in a counter current fashion. So this is liquid inlet and this is liquid outlet. Okay, in the gas, there will be solute plus carrier. So this solute has to solubilize inside this liquid according to the absorption operation. So to do that one, we have to bring this gas and liquid to the intimate contact. Okay, we will bring the intimate contact. For example, there are some 100 particles of solute. We will be measuring not in particles, in concentration. For your understanding, I am telling 100 particles of solute is there. Among this 100, how many are transforming into the liquid and how many are there in the outlet of the gas? Okay, 50 are transformed here and 50 are coming out along with the gas outlet. Okay, this we don't know. Gas we cannot see with our naked eye. How many particles are there? We cannot measure that one. Okay, with our naked eye. So for the time being, let us assume something is simple, uh, um, a simple fact. Okay, everybody knows this fact. They can realize, they can relate this with the real life problem. For example, you are sitting at some stream, some water stream, okay, using your boat. Okay, you are pedaling. Okay, know that boats normal pedal boats. So you are there in some water stream. Assume that you are there in a water stream and you are sitting at one place. Okay, at one place using your pedal boat. Okay, you are pedaling that boat. You are the one person, you are sitting here. Now you are interested. Okay, you are interested to study within a control volume. No system means nothing but what is the system? Definition of system is nothing but whatever we are concentrating, no, that is our system. Okay, if we can see, we can able to see the entire Hussain Sagar. Okay, that is our system. So but we cannot see entire Hussain Sagar at one glance. Okay, we cannot see that one. But if you are paying a keen attention, a small volume, small control volume only we can observe. For example, your control volume is this one. So you are interested to study a small part of Hussain Sagar. Okay, there you are sitting at a boat. Okay, on a boat you are sitting and you are observing in this you with your naked eye what is the concentration of fishes or how many number of fishes are coming with this control volume and leaving. Okay, for example, there are some fishes like this. take some other color. Okay, some fishes are there like this. Okay, now you are interested how many fishes are entering within this control volume and how many fishes are leaving within this control volume. That is also mass transfer. General macroscopic view I am telling for your understanding. So this one you just realize, you just try to correlate with the real situation. Okay, here one stream is there. So in this water stream, you are standing at one location and you are trying to observe a simple control volume where you can see at one glance. Okay, at a one glance, if you see this one, your fishes are entering inside and they are leaving. Now your concentration is entirely how many fishes are coming, how many fishes are leaving. For example, this is one fish, this is two fish, three, this is four, this is five, and this is six. Like this. When you are sitting, for example, you are sitting. This is a sailor. Okay, you yourself assume that you are Sri Lakshmi or you are Pavani. Okay, or you are Sultan. Something you assume. Okay, you are a sailor. Common name is a sailor. You are sailing inside this stream. Then your boat is at a stagnant condition. You are standing at one single place only. Okay, stagnant condition. You are not at all moving. Then your velocity, boat velocity will be some u naught is equal to 0. For example, u naught is your boat velocity or your movement velocity. So that will be 0. Why? Because you are standing at one single location and you are observing how many fishes are coming inside your control system and how many systems are going outside your control system. Then the flux is nothing but the amount of the quantity which is transformed from one place to another place, means the number of fishes which are entering into the system from this location to this location divided by per unit volume, per unit surface area per unit time. So that is nothing but flux. Okay, flux is equal to, according to our flux definition, which is moles per area per unit time is the flux definition. Or in our this macroscopic terminology, we can say the number of fishes entering from this point and leaving from that point. Number of fishes entering and leaving into our control volume divided by unit area of that control volume, then divided by time. So this is normally the definition of our fluxes. Now we can define the flux. You are standing at a single position. So Ni is nothing but your flux when you are at a stagnant position. Your u naught is equal to 0. You are not at all moving. And by this location, you are only keenly observing your control volume. Under this volume, the flux defined is called as a flux with respect to fixed coordinate. Okay, Ni means flux with respect to fixed coordinate or fixed reference framework. Fixed reference framework means first you are yourself adjusting at a some location. You need not to be here only. You can be here, but you have to be stagnant. You have to stand at one single point, one single place you have to stand, and you are keenly observing a control volume. So under such conditions, whatever the flux defined is called as a flux with respect to fixed point or a fixed reference framework or fixed point or fixed location. Then Ni is equal to, okay, we can define it in a normal quantity. If your flux is measured in mass, okay, mass flux, this one. So mass concentration is measured in rho I into, okay, the concentration, the velocity with which the fishes are moving. Okay, fish movement is there. So fish, when there is a speed of that fish, it is coming to the control volume and it is leaving the control volume. If they are moving only, we can observe them. How many are coming inside or how many are going outside. Then only we can observe. So this is Ui. Okay, fish velocity, this one. Ui or small u we can say minus u naught. Okay, this is your boat velocity. So we know that at fixed reference framework, your boat will have a zero velocity. So we can cancel out this one. We can write Ni mass is equal to rho I into Ui. Okay, mass concentration of your fishes into velocity of your fishes. Then Ni mole, molar concentration. This is molar flux. So this we can say Ci into Ui minus U naught. we already know when Ni is defined with respect to fixed coordinate system. So U naught is equal to 0. Then we have to write Ci into Ui, concentration, molar concentration of your fishes into speed of your fishes or velocity of your fishes. Okay, in this general sense, I am saying fishes. Okay, it will not be used in terms of fishes. Only the particles. We cannot visualize these particles, but we can visualize fishes here. So that's why I'm taking this example. Okay, do you catch my point here? What I mean to say?
Yes, sir.
Yeah. Okay, then. Okay, next example. For example, the same example I am taking to define Ji also. Okay, the same stream is there like this. Same stream is there. Same example. You are sailing on a boat. Okay, you are a sailor. Then now you are observing the same control volume, the amount of fishes which is coming, the number of fishes which is coming inside and leaving. Okay, this may be fishes you consider like this. Fishes are coming inside and going. The velocity of this fishes is nothing but ui. So velocity of u is nothing but your boat is nothing but u naught. Now you are not at a stagnant position. You are moving. Okay, your boat is moving. Your boat will have certain velocity. Why? Because it is moving to and fro. Okay, it will go against the tide or it will go again along with the tide. Okay, tides means this one alalu. In Telugu we will call it as a alalu. Okay, మీరు అలలకి ఎదురు ఇదొచ్చు లేకపోతే అలలతో పాటు వెళ్ళొచ్చు. Okay, you can move along with the tides or you can move uh, opposite to the tide. Okay, whatever the velocity depending on your boat speed. Okay, here what are the parameters defined? Parameter is one is your tide velocity, tide direction. Okay, how your tide is moving along with you. You are moving along with the tide or you are moving opposite to the tide. Okay, tide velocity, tide direction, and your boat velocity, boat speed. Okay, all these parameters will come into existence whenever you are moving. If you are stagnant, no velocity, nothing is affecting there. Okay, only tide velocity or tide direction will be there, but you are anyway holding at a single place. At one place only you are standing. But here it is not like that. You are moving. Okay, your boat has some speed and your tides will have some speed and your tide will have some direction. Okay, all these parameters will be coming to the existence. That then you are moving. No, that's why your velocity is not zero. But in the stagnant region, your velocity is zero. Under such conditions, so for example, he can move in this direction or he can move in this direction or he can move like this x, y, z direction, any direction you can move. Okay, that boat can move any direction like this. So all these parameters will be coming into existence whenever your boat is just moving. Under such conditions, whatever the fluxes of that fishes is defined is nothing but Ji. So Ji is equal to flux with respect to arbitrary coordinates. Arbitrary coordinate, or we can write arbitrary reference framework. Why we are writing arbitrary? So what is arbitrary means? It's jumbled. Okay, means see, you are moving this direction, that direction. There is no constant direction. You are moving in x direction. There is no criteria that you are moving only in the y direction. There is no. You are moving in z direction. No, you are moving any number of direction. Your boat can be moving any number of directions. When your boat is moving with the speed, the tide will change your direction. Okay, tide direction will be changed. Many things will be happen. Air velocity is there. Air will also be flowing on top of you. Okay, it will be causing some influence on the boat. Okay, any direction. That's why arbitrary coordinate. Then observer, whenever you are observing, no, initially when you are observing, your control volume is a constant. But now your observation, according to you, your glance of seeing that control volume will be different. Okay, you cannot accurately observe this control volume. Under such conditions, whatever the flux denoted is Ji, flux with respect to some arbitrary coordinate. It need not to be only x or y or z direction or theta direction. Any direction it can take. That's why we are calling this as a arbitrary coordinate system. Then we have to write Ji mass. So mass flux is equal to same. this one, mass concentration rho I into ui minus u naught. So here now this is arbitrary coordinate. That's why this u naught is not equal to 0, but earlier it is equal to 0 because it's a fixed coordinate system. But here it is arbitrary coordinate system. Then Ji mole. Okay, molar flux is nothing but molar concentration Ci into ui minus u naught. Under these conditions, these two are not 0. U naught is not 0 and ui is not 0. But whereas in the fixed coordinate system, u naught is 0. Simply it will be reduced to product of mass concentration into velocity or molar concentration into velocity. But it will have some definite value. Okay, that value we will see. Okay, until now, any doubts? Do you catch my point? What I mean to say with the fish example or boat example?
Clear,
Yes,
sir.
sir.
Yeah. Then if there is a time, I will continue. Okay, 10:23 only. We can continue, I think. Yeah. So see,
Yes, sir.
this will have. Yes, something you want to say? Yeah. Then this will have some meaning. Okay, this u naught will have here some meaning. So what is this meaning? Okay, in a system of any molar species. Okay, only I am telling that this is a fishes, but in real mass transfer there is no fishes. Okay, we will not do anything with the fishes, but with the particles, with the movement, with this molecular species. Okay, we cannot observe with our naked eye. That particles we have to deal. So in a system of the molar species move with respect to in a move in different average velocities. So see, for example, the fishes, same example you take, the fishes will move with a different velocity. This fish number 2 will have some velocity 20 meters per second. Fish number 1 will have 20 meters per second. We cannot guarantee that one. So this velocity, this fish will have a different velocity. This fish will have a different velocity. This fish will have a different velocity. Okay, they will have a different. Okay, this is stagnant. Okay, any of the case. Okay, these fishes will have an individual. They are depending on their velocity. They will be acting. It need not to be same. No fishes will have an identical velocity. We cannot say that will have a same velocity. They are moving arbitrarily with a different average, different velocity. So we have to take it average. And under this condition, this boat will have a 20. For example, boat we are seeing it is moving at 10 kilometers per hour. Okay, 10 kilometer per hour speed it is moving. But what about the tides? Tide will influence, air will influence, and many influences are there. It cannot move 10 kilometer. It can move more than 10 kilometer per hour, or it can move less than 10 kilometer per hour. We cannot say this is moving according to the motor set point. Okay, tides will have. We cannot control the tide movement. We cannot control the tide direction. We can control only our boat. Okay, that also dependent on your tides. Okay, that's why we will take as an average velocity. Everything will be averaged. Okay, we will define as a average velocity. So the fishes or the molar species are moving with respect to a different average velocities. So we will take this as a average velocity u naught. So there are three types of average velocities are defined. So one average velocity is a mass average velocity. When your quantities are defined with respect to mass quantities, it is mass average velocity. So that is u naught. So this one u naught mass I am writing. So that denotes mass average velocity. So that definition of mass average velocity is sigma I is equal to 1 to n, means one species to n number of species, number of fishes which are there inside. Summation of this one, mass concentration rho I into ui divided by sigma I is equal to 1 to n rho I. So this is a mass average velocity when the mass quantities are given. Then next quantity is molar average velocity. Molar average velocity. So this is u naught mole is equal to sigma I is equal to 1 to n. So in place of mass concentration, we will write molar concentration Ci into ui divided by sigma I is equal to 1 to n Ci. And the third quantity will be volume average velocity. volume average velocity. So it will be denoted by U naught volume is equal to sigma I is equal to 1 to n partial molar volume mu I into Ci into Ui, where nu I is nothing but partial molar volume. So in our mass transfer operations, instead of this quantity, we will use this molar and mass quantities very high. Okay, these two formulas are very, very important. Okay, molar average velocity and mass average velocity. Okay, this is important, but not that much used. Okay, I have not seen in any problem the usage of this one. But you remember this two is very, very important. Okay, the definition of this U naught is nothing but you can calculate depending on your quantities, whether you can use this one or this one. Anything you can use. Okay, is that clear?
Yes, sir.
Okay, then in the next class, we will see the relationship between Ni and Ji. What is the relationship between Ni and Ji? For example, in this slide, it is provided what is the definition of these two fluxes. Okay, this quantity, these formulas. Then in the next class, we will see, okay, every formula is here, okay, in this slide. Then in the next class, we will see what is the relationship between N and J. We will define and try to calculate, derive this one, most important. This whatever the small equations I have given now, that are big derivations, these two formulas. So that is very, very important. They are asking many times in the exams. Okay, until here, if you have any doubts, you just contact me or you just try to revise once again. If you understand this concept, then only this derivations will be easy. Otherwise, it is very hard. Okay, I hope no doubts from your side, and thank you for listening.
Thank you.